Welcome to Lesson 12, Newton's Laws of Motion. Today we explain why objects move the way that they do. Here's the plan for today. The first law: an object will stay at rest or keep moving at a constant velocity unless a resultant force acts on it. Read that carefully. It says a force is needed to change motion, not to maintain it. A spacecraft coasting through empty space needs no engine at all, it just keeps going. The property behind this is inertia, an object's reluctance to change its motion, and the more mass something has, the more inertia it has. That's why it's so much harder to get a lorry moving, and so much harder to stop it once it is. The second law is the one you use the most, and you may have seen already. In its full form, the resultant force equals the rate of change of momentum. We'll come back to that next lesson, but for constant mass it simplifies to the version that you know, F equals ma. And I want to underline one word, resultant. It is not a force equals mass times acceleration. It is the resultant force, the overall force, the net force after everything has been added up. Miss that word and you get all the equations in the questions wrong. A quick but vital distinction: mass and weight. Mass is the amount of matter in something, measured in kilograms, and it is the same everywhere you go in the universe. Weight is the force that gravity exerts on that mass, measured in newtons, and given by W equals mg. So, an astronaut has the same mass on the moon as on Earth, but weighs about a sixth as much, because the moon's gravitational field strength is weaker. Mass in kilograms, weight in newtons, and weight is a force. Here's the method for every F equals ma question, and it's always 2 steps. Step 1, find the resultant force. That usually means taking the driving force and subtracting all the resistive forces, drag, friction, whatever's opposing the motion. Step 2, divide that resultant by the mass to get the acceleration. Students who go wrong here almost always go wrong at step 1 by plugging in the driving force alone and forgetting to subtract the resistance. Find the resultant first, every time. This brings us to terminal speed, and the key fact is that drag increases with speed. So picture a skydiver. At the very start, they're slow, so drag is tiny. Weight dominates, and the resultant force is large, and they accelerate hard. But as they speed up, the drag force grows. This means that the resultant force shrinks, so the acceleration falls, but they're still speeding up, just less rapidly. Eventually, drag grows until it exactly equals the weight. Now the resultant force is 0, so by Newton's first law, the acceleration is 0, and they fall at a constant velocity. That's what we call terminal velocity. Finally, a real-world application: stopping a car. The total stopping distance splits into 2 parts. The thinking distance is how far you travel during your reaction time, before you even touch the brakes, and during that time you're still going at full speed. It scales with your speed and with your reaction time, so it gets worse if you're tired, distracted, or have been drinking. The braking distance is how far you travel once the brakes are on and you're decelerating. And here's the crucial bit: braking distance grows with the square of your speed. Double your speed and the braking distance quadruples. That's straight out of v squared minus u squared equals 2as. It also gets worse with worn brakes, bald tyres, or a wet or icy road. That's the end of the video. Really make sure you understand this topic, as it underlines so much of mechanics in physics. Next time we look at momentum, why it's always conserved, and why a longer crash is a safer crash. Thanks for watching, and check out my tutoring page below.